So in the last lecture, we have studied different types of feedback topology, also different types of amplifiers. So, we are applying negative feedback in the amplifier, and depending upon the feedback topology, you can uh, you can categorize amplifier, not only depending on the feedback topology, but amplifiers basically they are of four types. There are four types. What are those types? Voltage amplifier, current amplifier, transconductance amplifier, and transresistance amplifier. DSC students joins very late. I am going to stop the entries after 5 minutes. How you categorize these amplifiers? So when you say voltage amplifier, so we'll see what are the inputs and outputs. Input, output, and gain. When I say voltage amplifier, so input is voltage, output is also voltage, and therefore gain is AV, voltage gain, which is the ratio of output voltage to input voltage. So gain is indicated by AV, that is equal to output voltage upon input voltage VI. For a current amplifier, the input is a current signal and output is also current signal. Therefore, we define the gain as AI is equal to output current IO upon input current II. For a transconductance amplifier, the gain is represented by GM for transconductance. Transconductance is opposite of resistance. Okay. So this ratio, the gain is ratio of output current to input voltage. Remember, V to I ratio is resistance, I to V is a conductance. It is called as transconductance because the numerator is from output parameter of the amplifier and denominator is from input. So ratio of IO upon V in is your transconductance. So output is a current signal and input is a voltage signal in case of transconductance amplifier. And for a trans resistance amplifier, input is a current signal, output is a voltage signal, and its gain is indicated by Rm, trans resistance gain, which is the ratio of output voltage VO upon input current II. Got it? So there are four different types of amplifier. Now, we have also seen what are the four different types of feedback topology. So in the feedback, on the feedback, you have to remember two important things. This is amplifier and this is feedback network. So at the output of amplifier, what is happening is sampling, and at the input of feedback amplifier, what is happening is mixing. So there are two types of sampling. What are that? What are those two types of sampling?
Current sampling and voltage sampling.
Yeah, voltage sampling and current sampling. Similarly, there are two types of mixing. What are that?
Series
Series,
mixing and
series mixing and shunt mixing. Now, depending on that, so there are some derivations we have to derive. The derivations are very easy. I will remember you how to remember the effect of Ri and Ro on every topology. What is the effect of Ri and Ro on every topology? Remember, when there is shunt, uh, uh, just first of all focus on mixing. Okay, mixing is happening input at input side. Mixing is happening. Okay, and sampling is happening at output side here. Okay, sampling is happening at output side. So whenever you sample voltage, you connect the input of beta network and output of amplifier in parallel. Okay, now I will tell you that this beta network has its own resistance. Let's say this is input side of beta network. This is output side of beta network. So its resistance of input side of beta network, that is its input resistance, and output resistance of amplifier, they actually gets connected in parallel, right? So whenever the two things are connected in parallel, their resistances also get connected in parallel. And therefore, if you observe the net resistance of output of this amplifier, not RL, not RL, because of the parallel type of connections and in this particular voltage series feedback, the output of amplifier and beta network are connected in parallel. Therefore, the net output resistance of this complete amplifier is going to reduce. Okay, it's going to reduce. This is going to reduce because uh, whenever two resistances appear in parallel, so you are connecting two things, amplifier and beta network, in parallel at this side. So the net resistance of this voltage series feedback amplifier is decreasing. So you can understand whenever there is voltage sampling, where is another voltage sampling? In this amplifier, you will find voltage sampling. So whenever there is voltage sampling, the things are connected in parallel at the output. Okay, whenever there is voltage sampling, this is connected in parallel. Okay, so whenever in this type of feedback also, the output resistance, the net output resistance of amplifier decreases. Okay, is there any voltage sampling? This is voltage sampling, this is voltage sampling. So whenever there is voltage sampling, the net resistance of that particular feedback topology or that particular feedback amplifier decreases. Okay, now just look to the output, another type of sampling, that is series current sampling. So here in this amplifier, current sampling is happening. Here at this stage, current sampling is happening. Okay, so when there is current sampling, the amplifier and beta network are connected in series. Okay, so and now you can think that the output resistance of amplifier, input resistance of feedback amplifier, they automatically get connected in series. And when you connect two resistance in series, the total resistance increases. Therefore, net resistance of this topology increases. What happened? Net resistance of this topology increases. Output resistance increases. Here also, output resistance increases. So we have focused on output resistance, RO of this topology or this feedback amplifier, whether it will increase or decrease, that you can decide. Now let's talk about the input resistances. Okay. So can you tell me in which type of mixing input resistance will be increased? In which type of mixing the input resistance will be increasing? There are two types of mixing, series and shunt. Okay, so now in this case you will find there is series mixing. In this case also you will find that there is series mixing. So whenever there is series mixing, voltage signals are added, and whenever there is shunt mixing, current signals are added at a node. इथे नोड फॉर्म होतो, तर हा करंट आणि हा करंट हे दोन्ही, if you apply KCL, they get added. If you apply KVL here, the voltage gets added. So in this two topology, voltage series and current series, you see whenever there is series type of mixing, whenever there is series type of mixing, inputs are present in series, so their net resistance is additive, and therefore the total resistance of this type of feedback amplifier increases as compared to the resistance of this amplifier. Suppose initially या amplifierचं रेझिस्टन्स होतं R1. जेव्हा तुम्ही व्होल्टेज सिरीज फीडबॅक अप्लाय केला, when you applied voltage series feedback, its resistance and beta network's resistance, they are in series, so net resistance of this entire amplifier has increased as compared to its alone resistance. Here also net resistance is increasing. Okay, so this is Ri, this is Ri. Okay, now what about this? Which type of mixing is this? Which type of mixing is this? Which type of mixing is this? Yes. Hello. Am I audible? Am I audible?
Yes, ma'am.
Yes, yes, ma'am.
Which type of mixing is this? Series or shunt?
Sure.
Shunt mode.
So whenever there is shunt mixing, two resistances, the input resistance of amplifier and output resistance of beta network, they are mixed in shunt. So shunt means parallel. What will happen to net input resistance of this amplifier? कमी की
Decrease.
जास्त? Increase or decrease?
Decrease.
Decrease. It will decrease. It will also decrease. Okay. Got it? When the input resistance increases and when it decreases. So now we'll write a table based on this. So we have uh, different types of amplifier. So first letter of amplifier indicate what type of sampling is happening. So what type of feedback topology is used? So remember the name of amplifier. This is feedback topology. Which type of feedback topology is used? So the name of feedback amplifier is written as the first name indicates sampling. The first word from the name indicates sampling. Second word indicate mixing. So there are voltage series feedback amplifier. Okay, voltage series feedback amplifier. This indicate, first word indicates what type of sampling. Second indicates what type of mixing. Okay, then what is the effect on Ri and what is effect on Ro? when you apply voltage series for a voltage series feedback amplifier. Similarly, what is the second? Can you tell the name? Voltage series, voltage shunt. Third is current series, and last is current shunt. Okay. So whenever, now look at the first word which is indicating sampling. Sampling takes place at output. Look, voltage, it takes place at output. So I will write for output. Sampling, voltage. So it's the part of output. So when I see the first letter, I will comment. Here it is voltage sample. So I will say RO is decrease. Again, here voltage is sampled. I will say RO is decrease because voltage sampling happens in parallel type of connection. It's a current is sampled. So output resistance will increase. Current is sampled, output resistance will increase. Now I look at the second word, which is series. Whenever there is series type of mixing, Ri is going to increase. Whenever there is shunt type of mixing, Ri is going to decrease. Again series and again shunt. Okay, so this is how you have to remember. Have you understood? Got
Yes,
it?
ma'am.
Now when we say, and I will not go for the derivation, but you remember, important from MCQ point of MCQ exam viewpoint. Whenever I am saying input resistance is increased, okay, it increases by a factor D, which is called as D sensitivity. Okay, it increases by a factor D. Now what is that D? This D is equal to 1 plus beta time the gain of amplifier. 1 plus beta time gain of amplifier. Okay, that is the sensitivity factor. If you remember, we wrote 1 plus a beta, right? 1 plus a beta. So this is called as desensitivity. In the gain of amplifier, you have seen this 1 plus a beta appears. Okay, so this 1 plus a beta is called as desensitivity. So D is equal to 1 plus A beta. So look now, whenever I am saying gain is input resistance is increasing. Ri is input resistance. RIF is a notation indicating with feedback. Ri indicates without feedback. RIF indicates with feedback. In this slide, I have used this. So you please use in our whatever I have written in whiteboard, you can write there RIF and ROF. So when I say it is increasing, so original resistance Ri is getting multiplied. RIF means resistance with feedback. So when I say it's increasing, means original resistance of an amplifier without feedback gets multiplied by factor of D. Okay. So again, when I'm saying it gets multiplied, and when I say decreasing, like in voltage, I'm saying it is decreasing. So Ri gets divided by D. Ri gets divided by D. Okay. So from this, you can write the formula for input and output resistance. Okay. Whenever you say increases like this, when you say increases, so it gets multiplied. The original resistance without feedback gets amplified by factor of D in case of increasing. Okay, in case of increase. And when you say decreasing, then in that case, Ri gets, that is resistance of amplifier without feedback, gets divided by factor of D. Okay? It's get divided by factor of D. So by choosing proper feedback topology, you can have the desired input and output resistance. Suppose you want amplifier with very high input resistance and very low output resistance. So you can choose the combination. The gain we have already learned what is the gain. Now remember gain. When you apply negative feedback, there is only one disadvantage, that its gain decreases. Okay. So here we will be using notation AVF, GMF, RMF and AIF to indicate the gain. Now it's a voltage series, means a voltage amplifier. So gain with feedback we will indicate by AVF. Okay, gain with feedback will indicate by AVF. For current series, it's a transconductance amplifier, so we will indicate its gain by GMF. Similarly, for voltage shunt, which is trans resistance amplifier, will indicate by RMF, and current shunt, which is a current amplifier, will indicate the gain by AIF. So in all cases, the gain is getting reduced because of negative feedback. So the gain with feedback, that is AVF, is equal to AV, that is gain without feedback, divided by D. So in all parameters, the gain is getting divided by factor of D. Now just see about bandwidth. Because this is a negative feedback amplifier, when gain reduces, bandwidth has to increase. So for all four configuration, bandwidth BWF, means bandwidth with feedback, increases as compared to bandwidth without feedback. So this is bandwidth with feedback. How much it is equal to? Bandwidth without feedback multiplied by factor of D. So whenever we say increases, it gets the bandwidth or input resistance or that without feedback, that gets multiplied, and when we say decreases, it gets divided. So when we say noise is reducing, noise is decreases, means noise with feedback is equal to noise without feedback divided by D sensitivity D. Okay, so remember this relationship. Now look here, this is your one of the experiment number 3, current series feedback. Okay. Current series feedback. Now you have you're familiar with this amplifier. Now this is a common source MOSFET amplifier with voltage divider bias method of biasing. Okay, so you apply input voltage through capacitor, you take output voltage through a capacitor, you connect a bypass resistance to increase the gain. R1, R2 forms voltage divider network, and RS is the source resistance. RD is the drain resistance. Okay. Now, how current is, this is a current series feedback amplifier. Now, how you can say current series? So, I told you, first letter indicates what is sampled. Okay. So, this is indicating current is sampled. Okay. And the word series indicated how it is mixed. Okay. So current is sampled. So I should know which current is sampled. Now look here. This is the drain. Okay. The current which is flowing through drain is the drain current. Okay. This is drain current. Okay. Now this drain current, I have a switch here. Can you see there is a switch? There is a switch here. Suppose I close this switch, means capacitor is connected. Okay. And in that case, the current, the AC current which is flowing, see there are two types of current. Let's say I'm talking about AC current. So when I connect here a capacitor, this AC current is bypassed. This is a bypass capacitor. So AC current will pass through capacitor, because capacitor allow AC to pass. So its resistance is very low as compared to RS. So the entire current, AC current, will flow. So this AC current will not drop any voltage across RS. Because of this, what is going to happen? Your output is going to increase, your gain is going to increase, but now there is no feedback. Okay. In order to have feedback, what I am supposed to do? I will open this switch. This switch me open karnar. Okay. I'll open this switch. When I open this switch, स्विच ओपन झाली आता म्हणजे आता कॅपॅसिटर मधून करंट जाणार नाही. So when I open the switch, this current will pass through source resistance. Okay, so it will drop here voltage. Now this is nothing but my feedback resistance. हे माझं feedback resistance आहे. Okay, this is my feedback network, consist of RS. So current was flowing, some part of the current which was flowing through RS, I said we have sampled current. कुठला parameter sample केला? Currentचा. And because of this, voltage has dropped across RS. If you see the input, this is your input. The voltage between these two terminal is VGS. Okay. And this is ISRS. ISRS is approximately equal to RDRS because source and drain currents are same. Okay, almost same. So now what is happening here? The input voltage, the total voltage which is receiving to the MOSFET amplifier. हा MOSFET amplifier आहे. या MOSFET ला input voltage काय जाता है? So this VGS plus VS, it is receiving the voltage at the gate. MOSFET ला जे gate ला आहे ते voltage मिळतं. एवढं voltage MOSFET ला मिळत आहे between these 2 points. This is gate terminal. So from gate to ground it receives. Now what is this gate to ground voltage? It is equal to VGS plus VS. Okay. So VI is equal to VGS plus VS. This. Okay. So what is VGS? You can see VI minus VS. म्हणजे इनपुट इथे जे आहे टोटल गेटला काय जात आहे? VGS प्लस द व्होल्टेज ड्रॉप अक्रॉस RS. आणि व्होल्टेज ड्रॉप का तयार झाला? कारण आउटपुट करंट ह्याच्यामधनं फ्लो होता. So sampled is current and mixed in series because we are now adding two voltages, VGS and ISRS. So voltage signals are mixed, म्हणजे series mixing झाले and current is sampled. Okay. So when you open this switch, feedback takes place. When you close this switch, feedback is not there. Okay. So from we can calculate the input resistance, output resistance of this amplifier. There are different formulas to calculate and you have to perform the practical. In the practical, you have to find 3 readings, VO, VO dash and VO double dash. So for that purpose, we'll be using here input resistance and a RL. When you give input signal without RS and RL, that reading is called as VO. When you only connect here RS, that is when you give input resistance through RS, the output will be VO dash. And when you disconnect this RS and connect RL, your output measured is called as VO double dash. So you have to observe it in the practical and then you have to perform those calculations. Okay. Are you getting? I know we are on the fast track, but I hope it is clear to you. Shall we move further?
Yes, ma'am.
Now see, this is example of voltage series feedback. In the previous, it was a current series. We were taking the part of current to form the voltage. Now in this topology, this is called as you're taking output over here, not to the drain. इथे drain ला output नाहीये, तुम्ही source ला output घेताय. याला म्हणतात source follower circuit. जसं तुमचा common collector असतो, तसाच common drain पण असतो. So this is a common drain circuit and you are taking output over here. Okay. So the part of output the voltage is present, output is present across RS in this example. And the same voltage is getting mixed here. So this is VGS and this is your Vs. So output voltage is present across Rs. It is same as Vs, and same Vs you are mixing here. So this is called as voltage series. Series mixing लक्षात आलं तुमच्या? दोन व्होल्टेज सिग्नल मिक्स करतोय म्हणजे सिरीज मिक्सिंग झालं. लूप जेव्हा फॉर्म झाला तेव्हा सिरीज मिक्सिंग होतं. आणि नोड फॉर्म होत असेल, सपोज इथनं करंट आला आणि इकडनं पण तुमचं कनेक्शन आहे ज्याच्यामुळे करंट आलाय, तर नोड फॉर्म झाला तर करंट मिक्सिंग होतं, आणि लूप फॉर्म झाला तर voltage mixing होतं. So output voltage, the voltage which is present directly here, that is our feedback network. So this is voltage sampled and mixed in series. So this is voltage series feedback amplifier. Now I told you how to draw the small signal model. Unit number 1 मध्येच मी तुम्हाला शिकवलेलं आहे. So in the same way you can draw the small signal model. In this only to important thing to remember that if there is a resistance Rs present, so how it will appear? It will appear as a part on both the sides. Okay. So this is about feedback amplifiers. Now let's in fast discuss about the oscillator. You all are familiar because you are a diploma student. You have studied oscillator. Can anybody define what is oscillator? Can anybody define what is oscillator? Yes. What is oscillator? Student, please speak. Unmute yourself and tell me what is oscillator. Do you know it? Yes or no? Don't wait for others reply. Unmute yourself. Whenever I am asking you to unmute, remember you have to unmute and reply something, whether you know it or not. If you are
It produces waveforms.
correct, it produces waveform. Anyone else?
It produces repeated continuous waveforms.
Very good. Oscillator is a circuit which provides the oscillations. Okay, now the oscillations may be sinusoidal. So in that case, it is a sinusoidal oscillation, or it can be a relaxation oscillator, like if it is producing some sawtooth waveform, right? So there are different types of oscillators you can categorize, like you can call RC oscillator or LC oscillator. Okay, if you are using the feedback network with RNC, you call it as RC. If you use LC, you call it as LC oscillator. So high frequency oscillator, low frequency oscillator, radio frequency oscillator. You can have multiple categories of oscillator. Now just we have studied feedback amplifier. Okay, so if you remember, in the feedback amplifier also there was amplifier. Then there was a sampling network. We used to take some part of it. The beta network used to take some part of it and provide it back to the amplifier. So that way its circuit, its block diagram is similar, but only you find one thing missing, that there is no input signal. See, there is no mixer. There is no mixer. In case of feedback amplifier, there was a mixer and there was input signal Vi, right? In Vs signal. So we used to give a signal, then there was a mixer, the feedback signal, and this signal used to mix, and then we used to provide input to the feedback amplifier. But the difference in the oscillator and amplifier is that the very important difference, that oscillator does not require any external input signal. Got it? The main difference, oscillator does not require any signal, any external signal for start of its operation. So this is the basic difference. It does not require any input signal. So it has only the sampling network. Some part of output is sampled and directly mixed with the amplifier. Okay. This is the main difference. And in case of, now the question comes that amplifier has to amplify, then its output will be sampled, and then beta network it will provide to back to the amplifier. But how amplifier is going to start its working? Initially, when I switch on the circuit, without any signal, what things this amplifier will amplify, isn't it? Amplifier ला इनपुट सिग्नल दिला नाही, amplifier ऑन केल्यानंतर तो आउटपुट सिग्नल कसा देणार तुम्हाला? If it does not if it does not have, excuse me, okay, if it does not have any input signal, how it can give the output? So remember, very very important thing in oscillator, that the amplifier is of positive feedback. This amplifier uses positive feedback. For amplification purpose, we apply negative feedback because of its many advantage. Okay, but in oscillator, our amplifier uses positive feedback. Why? Because the gain of positive feedback is very high. This is the gain of positive feedback, A upon 1 minus A beta. This is very high, and when there is very high gain, see, output of any amplifier, output of any amplifier is equal to its gain times input. Because in positive feedback, this gain is very high, so a very small voltage, input voltage, makes that amplifier to provide output. Okay, high large output, छोटासा सिग्नल पण एम्प्लिफाय होतो, कारण त्याचा खूप जास्त एम्प्लिफाय होतो, कारण त्याचा गेन जो आहे खूप जास्त आहे. नाउ how this amplifier is going to start its working, हा कसा वर्क करतो? So initially, in any circuit there are the passive components like resistors. Okay, and you are also familiar with the term noise. Noise is present everywhere in the electronic circuit. Okay, and because of this noise, there is some noise voltage present at the input of amplifier. कशामुळे? Noise मुळे there exists some voltage at the input of amplifier, and therefore this small noise voltage is amplified by this amplifier, and it's provide VO. Once it provide VO, beta network take it some part and provide back to the input. Okay, so this way its initial operation is started. Once started, then the loop is completed, and continuously it will receive the input from feedback network, and it will provide output. Now when we look at this diagram, remember which type of feedback we use in oscillator. We use positive feedback. Why? Because the positive feedback gain is very high, therefore a small voltage gets amplified by a high gain value. How oscillator starts working initially without any signal? So it's a noise voltage present at the input of amplifier, which makes amplifier to start. Got it? 3 important questions based on this topic will be asked in practical examination. You have a Wien bridge oscillator also. Let's move further. When we talk about oscillator, there is an important criteria. You know this, Barkhausen's criteria. Okay. In the Barkhausen's criteria, there are 2 conditions. Now, what this Barkhausen criteria say? That you have made the circuit of oscillator. You say this is oscillator circuit, but oscillator shall provide us sinusoidal oscillation voltage with constant amplitude. Then only this oscillator is useful. Okay, then only this oscillator is useful. If I have a circuit which is generating such type of oscillation, continuously increasing, I can't call this as an oscillator. If I have circuit which is generating the output which is continuously decreasing and finally becomes zero, so this is none of my use. I want such type of oscillations, constant amplitude throughout. These are called as undamped oscillations, and these are called as damped oscillation. okay, whose amplitude go on changing, damped. Constant amplitude, undamped. So we want undamped oscillations. Constant amplitude असलेले oscillations आपल्याला हवे आहेत. So for that there is a criteria called as Barkhausen's criteria. So what does this Barkhausen's criteria state? Barkhausen's criteria states that there are two conditions. The frequency of oscillation is determined by the condition that the loop phase shift is zero. Now, I'll bet I will give you it in more easier way. So condition first say that the total phase shift around the network. This is a network, this is a closed loop. So according to Barkhausen's criteria, the total phase shift around this network. Now your signal is going to transfer from this point to the amplifier, then to the beta network, from beta network back to the amplifier. So when the signal is moving through this loop, the total phase shift of that signal should be, can anybody tell me if you remember? Total phase shift around the network should be 0 degree or 360 degree. This is your signal. Okay, this is your signal. When this signal start moving, so amplifier, if it does not provide any phase shift, the signal will like this. Beta network, in that case, your beta network shall also not provide the phase shift. The same signal shall appear. This is called like 0 degree phase shift. But suppose you have given this signal and amplifier has provided 180 degree phase shift. Okay, and तुम्हाला माहिती आहे की जर इनपुट सिग्नल आणि फीडबॅक सिग्नल याच्यामध्ये फेज शिफ्ट असेल तर तो निगेटिव्ह फीडबॅक होतो. आपल्याला पाहिजे पॉझिटिव्ह फीडबॅक. वी वॉन्ट पॉझिटिव्ह फीडबॅक, and positive feedback means input and feedback signal both should be in phase. Therefore, if amplifier is providing you this phase shift, your beta network shall also provide you phase shift. Okay, now this is the phase shifted signal of amplifier. If beta network also provide the phase shift, how the signal will look like? It will again like this. याचा परत phase shift झाला तर signal असंच होईल. आता 360 डिग्रीची झाली, 180 here, 180 here, totally 360. So in this case, this signal and this signal are in phase. This signal and this signal are in phase. So the first statement of Barkhausen's criteria ensure the positive feedback. Barkhausen's criteria, the first statement काय सांगते? Positive feedback amplifier. So the statement is total phase shift around the oscillator network as the signal passes from amplifier through the beta network back to the amplifier should be 0 degree or 360 degree. Again in simpler way, total phase shift around the network should be either 0 degree or 360 degree in oscillator. लक्षात राहील? And this ensures positive feedback. Now, another statement of Barkhausen criteria says that in order to get sustained oscillation, mod A beta shall be greater than or equal to 1. Oscillation will not be sustained. Sustained means constant. If at the oscillator frequency A beta is less or A beta is greater. Okay, so for the second statement, again I'll explain you. The second statement of Barkhausen's criteria simply says that mod of A beta, what is A? Gain of amplifier, the gain of amplifier without feedback, and gain of feedback network beta, its product should be greater than or equal to 1. So actually it should be A beta should be equal to 1. Mod A beta should be equal to 1. So that you will get sustained oscillation. But in fact, we adjust A beta slightly greater than 1 and then circuit itself adjusts the constant amplitude. What will happen if mod A beta is less than 1 or greater than 1? Suppose A beta, the magnitude of A beta is less than 1. So you will get this type of oscillations. How? The amplitude of oscillation will continuously go on decreasing. Finally, it will become 0. If mod A beta the mod of A beta, the product of A into beta is greater than 1, then what will happen? It will continuously go on increasing. Like this. Okay? We don't want this. But if mod A beta is equal to 1, if mod A beta is equal to 1, you will get the constant amplitude, sustained oscillations. That is, its amplitude will remain constant. Let's have one example. This is amplifier, this is feedback network. Okay. Let's say you have applied input signal of 0.1 volt. Okay. Let's say the gain of amplifier is 10. Okay. So what you will get at the output? 0.1 volt एवढा इनपुट दिला आहे आणि एम्प्लिफायरचा गेन 10 आहे, तर एम्प्लिफायरच्या आउटपुटला किती मिळेल? Is it a difficult question? What you will get? Yes, Shriram. Gain of amplifier is 10. You have applied input 0.1 volt. What you will get at output of amplifier? Shriram, are you there?
Yes, ma'am.
What will get at the output?
Can you repeat the question?
You have applied input voltage Vi equal to 0.1 volt. Gain of amplifier A is 10. What will be the output VO of this amplifier? Everything is written in front of you. This is not expected from you, students.
Ma'am,
1.
1.
1. Yes, correct. Because VO is equal to A into Vi. So you will get output equal to 1 volt. Now assume that beta, the feedback gain or feedback factor, is equal to 0.1. Okay, you got 1 volt here. Let's say 1 volt. Signal of 1 volt. Then suppose beta is 0.1. So input to the beta network is 1 volt. Whatever is the output, that will be input. So what will be the output of beta network? इथे किती मिळेल? Feedback voltage किती मिळेल? Beta is 0.1. Its input is 1 volt. What will be VF? Yes? Same. This is again, I am saying this is gain of feedback. Correct. 0.1. 0.1. 1 into 0.1 is 0.1 volt. Now remember, what is directly going to feedback? Initially 0.1 volt होतं. Feedback देऊन सुद्धा पुन्हा काय चाललं आहे? Amplifierला 0.1 चाललंय. Again, this, because its gain is 10, it is providing you 1 volt and the same process repeating. So every time you will get 1 volt, 1 volt, right? You will get. So if you see A and beta, A beta, what is A equal to? 10. What is beta equal to? 0.1. So mod A beta is equal to 1. That is why you are getting sustained oscillation. For example, now I'll take another example. Let's say again we have applied, this is 1, okay, and gain is again, let's say 10. So you will get output 1 volt. But this time feedback factor is, let's say, 0.01. एवढा आहे feedback. So what I will get at the output of feedback? I will get 0.01 volt. First time I got output 1 volt. So if I used to plot VO, I got output 1 volt. Okay, this is, let's say, 1 volt. Next time output of feedback nectar VF is 0.01. And the same is becoming input to the amplifier. म्हणजे next time amplifier ला काय गेलं? 0.01. ठीक आहे, 0.01 झाला आता याचा इनपुट. 0.01. Now what will be the output of VO? आता आउटपुट पहिल्यांदा 1 मिळालं तर आता काय मिळेल? 10 into 0.01
0.1.
0.1 volt मिळालं. बघा पहिल्यांदा 1 volt मिळालं होतं, आता डिक्रीज झालं. नाव आय गॉट स्मॉल आउटपुट. ओके, नाउ दिस 0.1 volt will go to the beta network. आता बीटा नेटवर्कला काय मिळालंय? 0.1 volt. Its gain is 0.01. What will be the output of beta network now? 0.01 into 0.1. 0.001. Okay, so again amplifier is receiving 0.001, so I will get output 0.01. आणखी कमी झालं. So this process will repeat and I will get the amplitudes which are continuously decreasing. Okay, why? Because A into beta is not equal to 1. A 10 आहे, beta 0.101 आहे, so A beta is not 1. Okay, it was less than 1. A into beta was 0.1, which was less than 1, so I got decreasing. If you can take one more example. Let's say again our input is 0.1, gain of amplifier is 10, I'll get 1 volt. This 1 volt will go here and feedback factor is, let's say, 10. Or let's say 1, because it can be maximum 1. Feedback factor I have 1. Okay, so 1 into 1, I'll get 1 volt. So next time amplifier will receive 1 volt. If it receive 1 volt, next time it will give me output 10 volt. Then beta network will receive 10 volt. It will give me 10 into 1, that is 10 volt. So next input to amplifier will be 10 volt. Okay, so next output of amplifier will be 10 into 10, 100 volt, right? So every time my output is increasing. First time it was 1, then it was 10, then it was 100, and so on. I am getting continuously increasing oscillation. Why? Because 10 into 1 is equal to 10. A into beta becomes 10, which is greater than 1. And that is why to get sustained oscillation, mod A beta must be equal to 1. Got it? Is it clear? What is Barkhausen's criteria? There are two statements of Barkhausen's criteria. First statement says the total phase shift around the oscillator network shall be 0 degree or 180 degree as the signal process through amplifier and beta network. This ensures positive feedback. And second statement says that mod A beta shall be equal to 1 to get the sustained oscillations. So now two types of oscillator we have to study. RC phase shift oscillator. In RC phase shift oscillator, now you need a amplifier and you need a beta network. This is the block diagram. So we need one amplifier and one beta network. So let's see what is there in RC oscillator. So we have an amplifier block charge. We are using a MOSFET as an amplifier because recently we have studied it. So this is a MOSFET amplifier with voltage divider bias method. Okay, so this is your amplifier. So A block hai, this is your amplifier. This is the output of amplifier. So this output of amplifier we are giving to the feedback network. And in case of RC oscillator, the feedback network is comprised of R and C. Okay, so 3 RC sections are there. See, you are using a common source MOSFET amplifier. So you know this amplifier provide you phase shift of 180 degree. Amplifier 180 degree phase shift deto. So now your beta network shall also provide a phase shift because you need total phase shift either 0 or 360 degree. So each of this RC section, एक R आणखी आहे याच्यामध्ये, so याच्यात swap झालेला आहे. So each of this section is providing 60 degree phase shift. Remember, you will say why you won't design a network with 180 degree phase shift. So it is very difficult to design, have the value of capacitors and capacitor to get exactly 180 degrees phase shift. So 60 degree is better and easier to form the RC network. So we use 3 such network. Each network is providing 60 degree phase shift. So total phase shift provided by beta network is also 180 degree. So 180 signal, suppose this is the input signal that is phase shifted here by 180 degree. This signal will go here, and when it passes through 3 RC section, again it will be shifted by 180 degree. Now your input signal and feedback signal are in phase. Okay, so this RC phase shift amplifier will provide you, RC phase shift oscillator will provide you the sustained oscillations. The feedback factor beta, remember this only, the feedback factor beta for RC phase shift oscillator is 1 upon 29. And you know, A beta जो आहे हा equal to 1 असायला पाहिजे. Mod A beta should be equal to 1. If beta is 1 by 29, then what shall be A? A must be 29. So that its product is 1. So remember, the gain of this amplifier, हा जो amplifier वापरणार, its gain must be 29 and the feedback factor should be 1 by 29. So that loop gain is equal to 1, A beta equal to 1. So in RC phase shift oscillator, remember, we are using MOSFET as an amplifier. MOSFET common source amplifier, and this amplifier provide 180 degree phase shift. The feedback network consists of 3 RC sections. Each RC section provide 60 degree phase shift. Thus, feedback network provide 180 degree phase shift. So total phase shift around the network is equal to 360 degree, which ensure first statement of Barkhaussen's criteria. Then for RC phase shift oscillator, the gain of amplifier must be equal to 29 and feedback must be equal to 1 upon 29 to have the second statement of Barkhaussen's criteria true. Okay, so this is all about RC phase shift oscillator. And असंच तुम्हाला Wien bridge oscillator सुद्धा आहे. Wien bridge oscillator, everybody of you are familiar with the Wien bridge. त्या Wien bridge ला 4 arms असतात. Okay, 4 arms are there. And these 4 arms, when these are the 4 arms. So पहिला arm मध्ये असतं RC, R and C connected in series. दुसऱ्या arm मध्ये असतं R and C connected in parallel. Then there are 2 resistances is another arm. Okay, so Wien bridge. So in this case, this is your Wien bridge. मी जे आता का ड्रॉ केलं होतं. So this is, let's say, A point, जिथे एक RC सिरीज मध्ये आहे. हा दुसरा आर्म आहे ज्याच्यामध्ये R आहे. तिसरा आर्म आहे ज्याच्यामध्ये RC पॅरलल मध्ये आणि हा चौथा आर्म. A, B, C and D. Okay, and this is an amplifier. Important question. Wien bridge provides 0 degree phase shift. Okay, Wien bridge provide, the feedback network is Wien bridge. It provides 0 degree phase shift. Therefore, your amplifier shall also provide 0 degree phase shift. But if you use MOSFET as a common source amplifier, it will provide 180 degree phase shift. Okay, Wien bridge 0 degree phase shift provide करतोय, पण amplifier जो आहे तो 180 degree phase shift provide करतो. म्हणून आपण 2 stages वापरतो. We use 2 stages. First stage give 180 degree. Second stage give again 180 degree. So total phase shift जी आहे amplifier ची ती झाली 360 degree and 0 degree phase shift by Wien bridge. So the gain of amplifier must be here 3 and beta shall be equal to 1 by 3. Okay, so this is about I know we are going on fast track. हे दोन्ही. In the next lecture, which we have at 3 o'clock, that is a practical lecture. So I will show you the practical of Wien bridge. Okay, only I will show you the practical of current series amplifier Wien bridge. एक practical आपण आधी घेतलेला आहे. 2 practical मी आज घेणार आहे. You have to see and then I will continue further part of this unit. Okay, so we'll stop here. Is it clear? You have to study whatever we are learning here every day. You have to learn it same day.